Okay, so this is kind of the next layer of the onion. It's one level deeper. So what we've focused on in the course thus far is entirely kinematics. So can we describe motion, right? We get to describe motion first in one dimension, then we learned through components we can use the same ideas in 2 dimensions. We've graphed things versus time. It's all about just can we describe motion? Do we have the language for it? It's like developing a new vocabulary. Now we get to see where do motions come from? Why do things move certain ways or not, and not in others? And this comes down to Newton's laws. Okay, so Newton's laws, there are 3 of them. I'm going to hold off on the third one and discuss it later so I can get into the bulk of the difficult stuff on homework number 4 earlier, which is all going to be about Newton's second law, really. What Newton's laws deal with are forces. So what forces are pushes and pulls on an object from the outside environment. Okay? And as you can probably imagine, it's going to be a vector because we're going to care not just how hard something pulls, but in what direction. Okay? So the first thing we have to establish before we start poking and prodding the object with forces is what is it that an object does when you leave it alone? So that's where the first law comes in. What is the natural state of an object? What is it that an object does or doesn't do when you leave it alone? Now, if you think you might have some intuitive grasp on this, it's not quite that easy because we live in a world where there's so many forces, nothing really ever gets to be truly alone, right? And so it can be more trickier than you might think to establish what would an object do if it was completely left alone. So, first I'm going to tell you the wrong answer. And the reason I'm going to tell you the wrong answer is because Aristotle came up with this thousands of years ago, and Newton corrected it hundreds of years ago, but people still today think Aristotle sounds more reasonable than what Newton said. So let me tell you what Aristotle said. And again, this is totally wrong. It is not correct. So here's the argument that Aristotle made. This was back in the days when they didn't really actually go out and do any measurements. They just philosophized and said, oh, that makes sense, as if nature might not have something illogical to say to what humans believe. Okay? Here's what Aristotle said. He said if you take an object and you put it at rest, it seems to stay at rest. So his idea was, I guess an object likes to stay at rest. So an object at rest stays at rest. So I guess I'll put it like this. An object at rest will remain at rest. But his reasoning was when an object is moving, it goes to rest. So you slide something across the table, it goes back to rest, so I guess it didn't like moving. There's something about that eraser that didn't like the motion, and it somehow sought a state of rest. So if you're in motion, you went back to rest. And so his reasoning was therefore that the natural state of objects is at rest, and if they're in that state, they stay that way, and if they're not, then they go that way. Now here's the problem with this reasoning. The problem with this reasoning is that the eraser, when I slid it across the table, did not come to rest because it somehow didn't like the motion, that there was something inherent in the eraser that didn't like moving. At this point, we know better. What is it that actually brought that eraser to rest? Friction, right? It was rubbing against the table, maybe air resistance. So when something is moving, it's not that it inherently naturally desired to go to rest, it's that we live in a world where when something moves, the outside world says, stop, we don't want you to do that. So you're going to have to do what Newton did, which was imagine a hypothetical surface with no friction, right? It's a hypothetical surface where if you put something on it, there's no friction to act as an outside pull to stop it. And there's no air. It's a perfect vacuum. So there's no air blowing across it. And if you can imagine that, then if you slid that eraser across the table, it would go forever. So Newton's correction was if an object is truly left alone, it actually will stay exactly in the same motion that it was already in if you don't have the outside world telling it to do otherwise. So it's not that at rest is the natural state. It's not that in motion is the natural state. The natural state is to do whatever you were already doing. So that's the essence. Objects like to keep doing what they are already doing. That's their preference. They don't have any preference for rest. They don't have any preference for motion. They simply have a preference for doing a moment later what they were doing a moment before. Okay? This concept gets a name. It's called inertia. Inertia is this idea that objects, and this is all objects, just like to keep doing what they are already doing. That object, an object like that would include yourself. Let me give you an example of inertia. Okay? So, let's say you're sitting on the couch. Well, what's one more TV show, right? I'm at rest. I want to stay at rest. Someone says, hey, let's go out. No, I want to sit here. Okay? So you want to keep at rest because you have been at rest. But if you're already out running errands, you're already going to the grocery store, whatever, going to the bank, what's one more errand? I'm already out, right? So you want to keep doing what you're already doing. Now, obviously, that's just an analogy, but you can take it even more literally. Let's say you are in a car and you're stopped. Your body wants to stay at rest. When someone hits the gas pedal, maybe you feel like you're getting thrown back, right? You might go like this. Back of your head might hit the car seat, right? Well, what's going on there is your body is at rest, so it wants to stay that way. It's not really that you're being thrown back, it's that the car is accelerating out from underneath you and says, hey, we're doing something else now, right? So your body wanted to stay at rest until the car told it, hey, let's do something else. But let's say you're now driving along the highway at 50 miles an hour. That's what your body wants to continue to do now, because that's what it was doing. So if someone slams on the brakes, right, you want to keep going and doing that, and hopefully you're wearing your seatbelt so they can say, hey, we're not doing that anymore, so you don't go through the windshield, right? So your body wants to stay doing what it's already doing, and so does everything else. Okay, that's the idea of inertia. Okay? So it might not seem like much of a correction, but Aristotle said that everything has a particular thing that it likes to do, which is being at rest, and if it's not that way, it goes towards that. Newton simply said, objects don't prefer to be at rest. They don't even prefer to be in motion. They just prefer to keep doing whatever it is that they're already doing. Okay? Does that make sense? Okay. So, we can actually consolidate this into a much more condensed statement because of the language we have from kinematics. When something stays at rest, its velocity is constant at 0. Right? And if something stays in the same motion, and I mean same in every sense of the word, right? I mean constant speed, so the speed is the same, and I also mean in a constant direction. Everything has to be the same. A constant direction, of course, is a straight line. Straight line. Well, this, of course, we have a quantity. Velocity encompasses both of these things, right? So if you have a constant speed and a constant direction, you have a constant velocity. So really all this boils down to is constant velocity. Constant velocity which happens to be 0 or a constant velocity that is not 0. Okay? So what is the natural state of an object? Constant velocity. If you leave an object alone, what would it tend to naturally do? It would naturally tend to keep doing exactly what it's already doing. Either a constant velocity of 0 or a constant velocity that's not zero, but nonetheless constant, which means constant speed and constant direction. Okay? So you will often hear Newton's first law. If you want to state it as the most laborious, long-winded statement, you say, what do objects like to do? Objects at rest will stay at rest. Objects in motion will stay in motion at a constant speed in a straight line. I don't know how many words that is, but it's a lot. Or you could say constant velocity, right? That catches it all. Okay? So let me show you examples of objects in these states. Now you might say, well, how am I going to really observe the natural state of an object when there are so many things in the outside world that tend to make an object influence it, right? So let me show you. So that eraser on the table, right? I put that eraser at rest on the table. Oh, it's still sitting there. Okay. There are forces that act on it. The force of gravity pulls it down. How do you know that there's something pulling down on it? Well, of course, if the table weren't there, it wouldn't just hover, right? It's going to be pulled downward by gravity. But there is a table there, and the table will hold it up. Because, of course, if the eraser were to fall down, then the table would be crushed. And this table doesn't want to be crushed. And so we have another force, which we call a support force, or sometimes we call it a normal force. In fact, we will more often call it a normal force for reasons that will become apparent a little bit later. You just realized you came an hour late? Okay. That's amazing. Sit there for 15 minutes before you realize you're in completely the wrong class. So there are two forces. So you can't really say that this object is left alone completely by the outside environment, right? There are two things that pull on it, but it's like a tug of war that no one wins, right? So these two forces are actually going to kill each other, and so the object doesn't actually do anything. It stays at rest. Okay? It's kind of like if you have a tug of war where there are two evenly matched teams, the rope doesn't move, right? The rope might as well be lying on the ground with nobody touching it, right? The rope doesn't move because one team isn't winning. So we want to really talk about not just are there forces, but is there an overall force? Is there any force left over after all the things start pulling against each other? And that's what we call net force. So the net force is the overall force that's left over. And here there is none. And that's the crucial thing. There's no net force. Okay? And if there's no net force, in other words, the environment is not instructing the object to do otherwise, it can stay in its natural state as according to Newton's first law. So this thing will stay at rest. Okay? Now, if you like, we can compare this to taking this eraser out to the deepest edge of space, far away from everything. I guess I can draw an eraser. There's some distant stars. This is my floating in deep space. Okay? If I released it from rest there, it would also stay at rest. Here, because probably it truly has nothing that is pulling on it, right? It's not near any planet that would pull it towards it. It's not on a solid surface that would push it. So here, the net force is zero as well. The net force can be zero because there are zero forces actually acting. Or it can be, the net force can be zero because there are two forces acting that kill each other, so why do they bother? Okay? In both cases, of course, it's able to stay at rest. Okay? You could have 17 forces act on something, but if they kill each other and there's nothing left over, then they might as well not have even bothered. Okay? So the net force is zero. In fact, when we're talking about the natural state of an object, what we really mean is that the net force is 0. So the environment does not exert any overall or net force on it, and if the environment does not exert any overall force, then we are free to watch its natural state. That will be a constant velocity of 0. In fact, that's really Newton's first law in a nutshell. Newton number 1 says if the net force on an object is 0, then its velocity will be constant. That is Newton's first law, written in a very concise, quick way. If you want, you can write an object at rest will stay at rest, an object in motion will stay in motion at a constant speed in a straight line unless acted upon by a net outside force. Or you can just say that, okay? So that's one example of an object that's staying at rest, which is definitely the more intuitive one. So let me show you an example of an object that stays at the same velocity that's not 0. Are there any questions before I do that? Yeah. Yes, so that's the next example I'm going to do. So this is the at rest, staying at rest state, and I'm going to do another one with an object at a constant velocity that's not 0. Okay, so sounds like we're ready for that. Let's do it. So I'm going to have an object in motion. Let's make it a car. It's got some velocity going down the straight road, okay? So let's tabulate here the same the forces. I guess I should do forces in different colors. So we do have a force of gravity. The road needs to be there to hold it up, right? But those two forces, just like before, cancel. So there's two forces that might as well not have even bothered. Okay? But of course, what we're used to is that if you're moving, then things start to conspire in our world to act against you. So example, for instance, would be the force of air resistance. Force of air resistance. There's certain forms of friction that could be acting against you. So there are things that act against you. So right now, that's a tug of war that's uncontested. And so, of course, that's where the car engine comes in. We have a forward force, which I'm going to say is, just because of lack of sophistication at this point, I'll just say it's the force of the engine. Okay? So the engine is going to have to supply a forward force. And those two, if those two cancel, then we once again have a net force of 0. So while we have 4 forces at least, depending on exactly how you count them, we still have a net force of nothing. And if you have no net force, then your velocity will stay constant. So you're going to stay at a constant speed in your straight line. So the very, very, very common misconception is that can the forward force of the engine, can that really be the same size as the backward force? Shouldn't the forward force be just a smidgen more? No. It's exactly the same size. What is it that keeps this car going when all the forces cancel? Inertia. The idea that objects will continue to do exactly what they're already doing if they're left alone. So the forward force and backward force cancel each other exactly. And what is it that keeps the car in motion? The fact that it was already moving, and so it wants to stay in that same motion. If you want, we can go back out to our interstellar space here, far away from anything. We're going to throw the car off a spaceship. And then leave. So we have a car flying through interstellar space. Here, there is no force of gravity downward. There's no planet to pull on it, so we don't need it to be on a surface to hold it up. There is also no backward force. There's no air resistance or anything conspiring to stop it, so we don't need the engine to be on. Not that it would do much, because there's no traction. There's nothing for the tires to spin against, right? So here, with zero force, we once again have zero net force, now because there are no forces at all, and therefore it'll just keep going forever at a constant speed in a straight line simply due to inertia. So we are so accustomed to being in a world where the moment you start moving, there are things that act against you. But the thing to realize is if you don't have anything against you, you don't need anything to keep the motion going either. Okay? It's the object's natural tendency to want to keep doing what it's already doing. So again, make sure you understand the force of the forward force here is not need to be more than this. It has to be exactly equal to this. So the net force can be zero, so the velocity will then be maintained just through the inertia. Are there any questions on this? Okay, so that is Newton's first law. And I'm guaranteeing you at some point in the semester, somebody in this room is going to get tripped up because they're going to see a velocity that's constant and go, I don't know what the net force is. It's zero. If the velocity is constant, net force is zero. Okay? So let's move on to Newton's second law. First law kind of sets the stage. The first law says, what do objects do if you leave them alone? Now we're going to start poking and prodding them and finding out how they react. If Newton's first law, I guess I'll just recopy it here, says if F net is zero, the velocity will be constant. The second law has the obvious conclusion, if the net force from the outside environment is not zero, what do you think is going to happen to the velocity? It's going to change. If the net force isn't constant, the velocity won't be constant anymore. We have a quantity from kinematics whose whole job is to talk about how the velocity changes. What is that? Acceleration. So there is some connection between net force that acts on an object from the outside environment and how it accelerates. So this is the net force on the object from the environment. And this will be the object's acceleration in response. That's where acceleration comes from. Well, we were certainly talked about acceleration and describing it. We did not talk about why do certain things accelerate and other things don't accelerate. Well, here we're getting into that idea. Why do things accelerate? Because they experience the net force from their environment. Why don't other things accelerate? It's because they don't experience the net force from their environment. So there's a direct tie-in between the pushes and pulls on an object from the outside environment, and again, we look at the net force. They can play tug of war. Maybe there's no winner, and the net force is zero. Maybe there is a winner, and we do have an overall force left over. And if we do have an overall or net force left over, the object will accelerate in response. The law itself is this. This is Newton's second law, and it is at the heart of Newton's laws. Okay? It tells us the relationship between the net force on an object and the acceleration it experiences, with the third ingredient being the mass of the object. Haven't done anything with mass yet. Here's our first introduction where mass might be useful. So let's take a look at the features of this equation. First of all, the formula, and again, because we don't do this hugely mathematically sophisticated. This may not be totally obvious, but the direction of the net force and the direction of the acceleration are always the same. Okay? So the net force and acceleration are always in the same direction. Okay, so you think of it as a tug of war, but now instead of the two sides being tied, one force wins, right? So one side wins. If the one side pulls harder than the other, which way does the rope go? It goes toward that side, right? So the direction of the net force is the direction of the acceleration. The other ingredient here is mass. Okay, so let's throw this in. Let's put in a small mass and a big mass. And let's suppose that they experience the same net force from the outside environment. So F net is the same on both. So let me draw in an arrow. It's going to be a vector. I'll try my best to draw it the same length. F net, F net. I don't think those are about the same length to the best of my ability to represent that they are the same amount of force, right? Same amount, same direction, same everything. But on the right-hand side, it's the product, right, of the mass times the acceleration. So two numbers which have to multiply to the same thing because the net force, I've said, is the same. Now, if you have a small mass, I'm going to need a big acceleration to get to that number. Whereas, if I have a big mass, I'm going to have to multiply it by a small acceleration to get to the same number on the left-hand side, right? So what that tells me then is that just because you exert the same net force on two different objects, it doesn't necessarily mean they'll react the same. This is a small mass, and so it'll experience a relatively large acceleration, a large change to its motion in response. Whereas, since this mass is very large, the acceleration is much more comparatively tiny. Now, this probably gels with your everyday experience, right? If you run at full speed and try to exert as large a force as you can on, say, a gigantic bookshelf with a lot of mass to like a tiny something, you're going to get a different reaction out of them, right? If you apply the same amount of net force on a very large mass, you don't get much of a change at all, right? It might budge a little bit. You might get a little acceleration, but not much. Versus if you apply that same effort towards something that's very small mass, you'll get a much more larger change to its motion, right? A much larger acceleration. Does that make sense? Okay. In fact, mass is a measure of inertia. So we talked about that inertia is this idea that objects like to keep doing what they're already doing, right? Well, if we have a larger mass indicates a larger inertia. Which is to say that it wants to keep doing what it's already doing more, right? So if all objects like to keep doing what they're already doing, if something has a larger mass, it wants to keep doing what it's already doing more. So it wants to resist your changes that you're trying to make. Okay? So a larger mass basically means more stubbornness to change. Stubbornness to change. A larger mass is more stubborn to any changes you'd want to make to it. Mass is the measure of that. So that's what we have here, right? If something has large mass, it's incredibly naturally stubborn to changes, which means that you're not going to get it to be able to change very much for your efforts. Okay? Mass is our measure of how stubborn something is to changes to its motion. Everything that has mass is stubborn to changes, right? It wants to keep doing what it's already doing. And mass is a measure of just how stubborn it is. Okay? With larger masses accelerating less. Okay? Are there any questions on that? Okay, so the one order of business we have left in Newton's second law, really. First of all, I will note that the information in Newton's second law, in the first law, is actually contained in the second law, right? If the acceleration is 0, what's the net force? 0. If the net force is 0, the acceleration is 0. If the acceleration is 0, what does that mean about the velocity? Constant. So the first law is in the second law. So Newton's second law is really the whole thing right now. It's everything we've talked about. It contains everything we've talked about today. You might wonder, why is the first law mentioned at all if it's really just a special case of the second law? It's because it really hammers home what is it that objects do when you leave them alone. Okay? But there is no mathematical information in the first law that isn't already in that second law. Second law can handle if the net force and acceleration are 0 or they aren't 0. Okay? So that's one thing I wanted to point out. The other thing we should talk about is the units of force. So, of course, any valid equation must be what we call dimensionally consistent. The units have to match. What are the SI units of mass? Kilograms. And what are the units of acceleration? Meters per second squared. So the units of force are kilogram meters per second squared. We give this a name because it's a pain to write all out. We call it a Newton. Not surprisingly, because, of course, these are Newton's laws. The unit of force is a Newton. Let me try to give you a sense of what 1 Newton of force means. 1 Newton of force, one way to visualize it, it's the amount of force it takes to take 1 kilogram and accelerate it by 1 meter per second squared, or I'll write it there in the more conceptual way, meters per second per second. So let's imagine this, okay? I've got a 1 kilogram mass in my hand. That's about 2.2 pounds on Earth, okay? I can hold a kilogram in my hand. Now, I am going to change its motion. So what I'm going to do is I'm going to take it from rest. I'm going to accelerate it. I'll do it to the side so gravity doesn't get involved, okay? And I'm going to take it from rest to a velocity of 1 meter per second in a 1 second time span. So 1 Mississippi and then 1 meter per second. That's about 2 miles an hour, okay? So 1 Newton of force would be the amount it would take for me to take that 1 kilogram mass in my hand and make it go from rest to 1 meter per second, 2 miles an hour roughly, in 1 second. Not a lot of force, right? You can easily exert 1 Newton. 1 Newton is an easy amount of force to exert, okay? That's kind of one way of visualizing what a 1 Newton is. 1 kilogram mass will not accelerate itself. It will accelerate itself if you apply a force. Okay? Okay. Any questions on that so far? All right. It may surprise you to learn that this law is pretty much going to be the main subject of homeworks 4 and 5 And we won't really introduce much of anything completely new through the first exam. You might wonder, how can we possibly spend many, many weeks on this simple law? It's 3 ingredients, right? So here's how. Let me kind of put together the thread of logic that this all goes through. The heart of the process is Newton's second law. Newton's second law is what tells us how to connect the net force on an object from the outside environment to how it reacts, how it accelerates in response. On one hand, this is our gateway to kinematics. If we are lucky enough to have a constant net force, then that will imply that we have a constant acceleration. So if someone hands you the net force on an object and then gives you the mass, you can compute the acceleration rather than being handed it on a silver platter like you were with homeworks 1 through most of homework 3. So you now have the capability to compute your own acceleration. And that, of course, can go into the kinematics. If you have constant acceleration, you can go to the constant acceleration equations. So remember, this is all building on itself. So now we can still use all our kinematic stuff from the earlier homeworks, but we now have the additional capability of computing our own accelerations. Now, this does require that the acceleration is constant, right? That's why they're called the constant acceleration equations. They don't work unless you have constant acceleration, smooth velocity changes. What if it isn't? So what do we do if we have a non-constant net force and acceleration? Well, that actually comes much, much later in the course. We use something called the energy method. I think that's homework 7 or 8 maybe. We'll come back to that later. So you can see it's a powerful equation in that it allows you to compute your own acceleration. But we do have a chain of logic over here too. Remember that the net force is the overall or net force from the outside environment. That could be due to 17 different forces pushing and pulling in weird ways, and you have to figure out, do they kill each other, or is there something left over after they have all done fighting? So one of the things you have to do is learn how to combine individual forces into this net force. How do you find the net or overall force if you have a bunch of individual forces? That, by the way, will be your lab exercise next week. You'll be learning about the vector addition of forces. I'll talk about it in lecture before then, but the very next lab in the lab manual talks about that box right there. Now, we have to back it up even one more step. If you're going to combine a bunch of individual forces into this net force, you have to know what they are. So we will learn to identify ID individual forces. So we'll learn about common forces that act and learn about what's their general nature like, so that we don't have to get handed those. We can just look at a situation and go, aha, I know that gravity acts. That's one of the forces we'll learn about. Maybe there's a string attached to your object. Then we have another force called tension. It's a force from a rope or a string. I mentioned earlier about the support force from a solid surface. So you have a solid surface that the object is touching. We call that a normal force. We'll learn about that. We'll also learn about friction. That's an important force. Whenever something is sliding along a surface, or even just on a surface, we have to account potentially for friction. And that, by the way, is the group of forces that we will learn about for homeworks 4 and 5 in exam number 1. So these will appear on homeworks 4 and 5, and it will be the cutoff point for exam number 1. So you can see that this is all kind of one interwoven tapestry from beginning to end. You can learn to identify the individual forces rather than being handed them. You can simply know enough about how they act to know what's going on. You combine them into an overall force. If there's any overall or net force left, it'll cause the object to accelerate. And of course, it depends on how much the object naturally tends to be able to resist that acceleration, which is its mass. And then you can tie that into the motion. So constant acceleration equations, if you have lucky enough to have constant acceleration, or later on we'll learn about the energy method. This is not on exam 1. That's actually exam 2. So this is all one interconnected thread, and in fact, while it might be nice to think that we're always going to start on the left and end up on the right, I should really put arrowheads double-sided on all those boxes, because of course we can always work the logic backwards, right? We could, for instance, solve for the acceleration, infer the net force, find out what individual forces contributed to that, and work backwards to a missing force or something like that. It's all one thread, so you can come in anywhere and take a left turn or right turn and work your way around, right? It's like coming into a maze from any place and working your way to any other part. I will give you a problem-solving strategy for this. At least for this part right here. I already gave you a problem-solving strategy for the constant acceleration equations. I'll give you another problem-solving strategy for forces. It's basically this, except for it's a much more nuts and boltsy kind of thing. It's like, hey, if you're attacking a problem, the first thing you should probably do is this, then do this, then do this, then do this, and it'll get you through, okay? So I'll give that. I won't have a chance to do it today. I want to do an example problem first where you kind of see how it goes, and then all the steps will make sense. Why do you do that first, then that, then that, then that? It's going to be too abstract if I just jump out with it, okay? So let's take a look at what we've done so far. This, of course, homeworks 2 and 3 was all about this. I think you have one question on this on your end of your homework 3, very straightforward, where you just tie this into this. We've already talked about this. Now, we need to talk about how might you combine individual forces into a net force. What's the process like?